Hello all, welcome to this beginner-friendly course on LLMOps from Simplilearn. So as large language models become more powerful, managing them efficiently in real-world applications is crucial. So this course will guide you through the essential concepts and practical steps needed to optimize, automate, and deploy LLMs effectively. So let's go through the agenda of the course. We'll begin with the basics of LLMOps, helping you understand its role in streamlining AI model workflows. Next, we will cover data preparation, where you'll learn how to clean, structure, and preprocess data to enhance model performance. Moving forward, we'll explore pipelines for orchestration and automation, ensuring that your workflows are efficient and scalable. And finally, we'll discuss deployment strategies, focusing on running LLMs in production while maintaining safety, responsibility, and ethical AI practices. And by the end of this course, you'll have a solid foundation in LLMOps, equipping you with the skills to optimize, scale, and manage large language models effectively. So let's get started and dive into the world of LLMOps. So imagine that you have built an impressive AI chatbot powered by a large language model. It answers customer queries, generates content, and even assists with coding. But here's the catch. How do you ensure it remains accurate, reliable, and scalable over time? So this is where LLMOps comes into play. So LLMOps, or large language model operations, is an extension of MLOps, or machine learning operations, which is specifically designed to handle the unique challenges of deploying and maintaining LLM-driven applications. In this chapter, we will explore the fundamentals of LLMOps and its importance in managing large-scale AI-driven applications. So we will begin by understanding the concept of MLOps and how it provides the foundation for LLMOps. Next, we will examine the MLOps framework, discussing key stages such as data management, model training, deployment, and continuous monitoring. We will then compare traditional MLOps versus LLMOps, highlighting the unique challenges that arise when working with large language models. Following this, we will illustrate the workings of an LLM-driven application with a high-level example demonstrating how LLMOps process user queries, generate responses, and improve through continuous learning. And finally, we will break down the LLMOps pipeline, explaining each step in detail. So by the end of this chapter, you will have a clear understanding of how LLMOps enable scalable, reliable, and efficient management of large language models in real-world applications. So let's get started. Let's start with what is MLOps. So MLOps, the short form for machine learning operations, is a set of practices that bring DevOps principles to machine learning. It focuses on automating and streamlining the life cycle of machine learning models, from development to deployment and maintenance. So the goal of MLOps is to ensure that machine learning models are not only built, but also deployed efficiently, monitored for performance, and continuously improved based on real-world data. So basically, MLOps bridges the gap between data science and software engineering, allowing teams to manage machine learning models just like traditional software applications. This involves practices like version control, automated testing, continuous integration and deployment, which is CI/CD, and performance monitoring. And one of the biggest challenges in machine learning is that models can degrade over time due to changing data distributions, which is also known as model drift. So MLOps provides a structured approach to detect these drifts and trigger retraining workflows to keep models updated. It also ensures that models remain compliant with data governance policies, improving their trustworthiness and reliability in production environments. So now let's see the MLOps framework. So the MLOps framework consists of different stages that enable smooth deployment and management of machine learning models. It starts with data management, which involves collecting, cleaning, and preprocessing raw data before feeding it into the model training pipeline. So proper data governance ensures that the model is trained on high-quality, unbiased data. Now, once the data is prepared, the next phase involves model development. Data scientists experiment with different machine learning algorithms, tune hyperparameters, and validate models to select the best performing one. Version control is very critical at this stage to track changes and improvements in model performance over time. Now, after selecting a suitable model, the deployment phase begins, which involves packaging the model into a deployable format and serving it as an API or integrating it into a larger application. Containerization technologies like Docker and Kubernetes are often used to ensure scalability and reproducibility across different environments. And finally, once the model is deployed, it requires continuous monitoring and maintenance. Performance metrics are tracked in real time to detect anomalies, and feedback loops are integrated to retrain and improve the model over time. This ensures that the deployed model remains effective and adapts to the evolving business needs. So next, let's compare the traditional MLOps versus LLMOps. So as you can see, traditional MLOps focused on structured datasets and smaller machine learning models, whereas LLMOps extends these principles to handle the complexity of large language models. LLMs such as GPT-4 and Palm required vast amounts of computational resources, larger datasets, and specialized deployment strategies. So unlike traditional machine learning models, LLMs are often used in open-ended tasks like text generation, code completion, and conversational AI. This makes their design fundamentally different from structured machine learning models that deal with classification or regression problems. LLM systems need to handle unstructured data like text and images while ensuring coherence, factual accuracy, and responsive relevance. Now, another key distinction lies in deployment strategies. Traditional machine learning models can often be deployed on standard CPUs and inference engines. In contrast, LLMs require GPU clusters, TPUs, or distributed computing frameworks to handle large-scale processing. Optimizing inference for LLMs involves caching, token-based batching, and using model distillation techniques to reduce computational costs. And moreover, LLMOps introduces additional challenges such as hallucination detection, prompt engineering, and reinforcement learning with human feedback to refine model behavior. So the governance and monitoring of LLM-based applications must account for these unique challenges to ensure high-quality responses and prevent misuse. So now let's move on to an example of an LLM-driven application. So with this example, you can better understand how LLMOps works. So this is an example of an AI-powered customer support chatbot for an e-commerce company. So when a customer visits the company's website and asks, "Where is my order?" the chatbot must understand the intent behind the query. So it first uses natural language processing or NLP techniques to extract the main keywords and determine that the customer is requesting order tracking information. So the chatbot then queries the company's order management system to retrieve the latest tracking details. So based on this information, it formulates a response like your order so-and-so is currently out for delivery and will arrive tomorrow or something like this. So the response is not simply pulled from any random predefined database, but it is generated dynamically by the LLM, ensuring natural and context-aware communication. So as you can see, the key aspect of LLMOps in the scenario is continuous learning and adaptation. So if multiple users provide feedback that the chatbot is making errors in tracking updates, the LLMOps pipeline ensures that these errors are analyzed and the model is fine-tuned to improve accuracy over time. Additionally, A/B testing is used to evaluate different variations of responses and improve user engagement. Now finally, let's move on to the LLMOps pipeline. So as you know, everything in LLMOps begins with data. And in this course, we'll start by preparing datasets and maintaining version control to track changes over time. And after that, we'll design a supervised fine-tuning pipeline for a large language model. While it may seem like a simple process, a lot of complex tasks are automated within this pipeline. And after fine-tuning, the pipeline produces an artifact, which is essentially a file containing key details about our configuration and workflow. So the workflow outlines a sequence of tasks such as step A, step B, step C, etc., while the configuration specifies parameters such as which dataset to use for fine-tuning. And once the artifact is created, we execute the pipeline, which not only fine-tunes the model, but also deploys the LLM. And once deployed, we can generate predictions by providing prompts to the model and analyzing its responses. And an important part of this process is the responsible AI, which involves assessing safety scores to ensure that the responses align with ethical and safety standards. So there are two essential components of LLMOps. First one, orchestration, which is managing the sequence of tasks, such as preparing datasets before fine-tuning and deployment. And the second one is automation, which is streamlining the pipeline to reduce manual effort and improve efficiency. So this LLMOps pipeline serves as a high-level framework, but depending on specific use cases, it can change. So that was it in this chapter. In the next chapter, we'll start with data preparation. So one of the most important parts of working with large language models is handling large amounts of text data. And in this lesson, you will learn how to pull text data from Stack Overflow stored in a data warehouse. So since this data is too big to fit in memory, we'll use SQL to manage and retrieve it efficiently. You'll also see how to modify the data to fine-tune a model, making it better suited for a specific task. So before we start, we have to set up the project environment, and first we have to load the credentials and relevant Python libraries. And if you're running this locally, you have to first install Vertex CI. Here we have already installed it. And before we start using Vertex CI, we need to set up authentication and configure the Google Cloud Project. So basically, Google Cloud Project helps organize all your cloud resources, including datasets, models, and other services you'll use. So you can think of it as a central hub where everything related to your AI work is managed. So now let's get our authentication code. So this is our authentication code. Import, authenticate, credentials, project ID is equal to authenticate. Let's run this. So this step is important because it verifies that we have the right permissions to access and use the Google Cloud services. So the credential variable over here is our authentication code, which is responsible for authenticating us. So basically it acts as our key to interact with the Vertex AI and other cloud resources. Now the next step is we need to choose a region, and this is basically where your AI resources will run. So you can think of it as picking a data center location for your operations. So for example, if you want to run your project in Germany, you might choose a European region like Europe West 3, which is Frankfurt, etc. So here we'll be using the US Central 1, which is our default region. This means that our AI tasks will be handled by a data center in the central United States. So let's write that. Let's define the region. Region is equal to US Central 1. So now let's bring in the Vertex AI library. So this library is what allows us to connect with the Google Cloud's Vertex AI services and use its powerful AI tools. So for that, let's give import Vertex AI. After that, let me just write the code. Vertex AI. Project is equal to project. Location is equal to region. Credentials is equal to credentials. So as you can see, to get started, we need to initialize the Vertex AI SDK. So these are the things that we provided. First, we provided the project ID. So this tells Vertex AI which Google Cloud project to use. Next, we specified the region. So this specifies where our AI resources will be running. And then we provided the credentials. These ensures that we have the right permission to access Vertex AI. So now that we have got everything set up, we are ready to dive into the data. So here we are going to use a data warehouse. So basically a data warehouse is like a central hub where you store and analyze large amounts of data from different data sources. So it helps businesses gain insights and make smart decisions. So imagine you have an application database, so you can pull that data into a warehouse, making it easily accessible for your teams. And for this, we'll be using BigQuery here, which is Google's data warehouse. So it's serverless, meaning plus it supports SQL, making it easy to work with. So as you know, SQL is built for handling large-scale data efficiently, and it's great for cleaning, transforming, and preparing data. And you also know that pandas work well with data fits in memory on your local machine. So SQL plus a data warehouse is a powerful combination, especially when working with large-scale MLOps systems for training and managing large-scale models. So first we'll import the BigQuery library and then we'll initialize the project while making sure we are using the correct credentials. So this setup allows us to interact with BigQuery and run queries on our data warehouse seamlessly. So let's write the code. Let's import BigQuery from Google Cloud. So from google.cloud import BigQuery. Q is equal to BigQuery client is equal to project ID credentials is equal to credentials. So as you can see here, we have imported the BigQuery and initialized the project. So now next in this course, we'll be working with the Stack Overflow public dataset. And this dataset contains questions, answers, and metadata from Stack Overflow, making it a great resource for exploring and analyzing real-world discussions. So basically, here's how the data is structured. At the top level, we have the Stack Overflow dataset. And inside this dataset, there are multiple tables, each containing different types of data. So let's write the code. Okay, there is some issue. Let's resolve this. So now let's write the code. And our query job is equal to tables. So since we are working with SQL, we'll use it to query the data warehouse. And one of the things we can do with SQL is explore the dataset by retrieving a list of all available tables. So for this, we'll run a query on BigQuery's public Stack Overflow dataset to fetch the table's name. We'll do this by selecting the table names from the dataset's information schema. This way, we can only get the table names without any extra details. And to send this query to the data warehouse, we'll use the client we just set up, and this will allow us to interact with the BigQuery and fetch the data we need. So now the BigQuery client works like a messenger. It takes the SQL query, sends it to the data warehouse API, and then bring back the results right into the notebook. So now let's just check the result. So that for row in query job for value in row dot values print value. So as you can see, we'll go through each row in the query job where each row represents a table name, and by printing each row, we'll get a clear view of all available tables. So we'll loop through the results and display each table name one by one. So as you can see the result, as we run and we got the result, we'll see a long list of available tables. So there are quite a few of them like answers, as you can see answers, questions and comments. And since we are focusing on fine-tuning, we'll be doing both parameter efficient fine-tuning and supervised fine-tuning. So to get started, we need to create a dataset first that pairs questions with their corresponding answers so that the model can learn from them. So now let's pull some data from our data warehouse and take a look at it. We'll run a query, load the results into a pandas data frame, and then visualize it right here. So let's write the code. The retrieval. So we'll be working with the Stack Overflow dataset. As you can see, the Stack Overflow dataset, specifically the post questions table. As you can see, post questions table. And our goal is to fetch all columns from this table. But we don't want to grab everything, just a limited number of rows. This helps us avoid pulling in too much data at once and making it easier to explore without slowing things down. So let's run this. Yeah. So as we told earlier, we'll load the results into a pandas data frame. We'll execute the query by sending a SQL command to the data warehouse and retrieve the data. So let's write the code. First import pandas. Pandas as PD. Next query equal to So as you can see, the next piece of code will take the results of a query from the data warehouse and load them into a pandas data framework. So let's write this down. So to make this process efficient, we first load the query results into an arrow table. As you can see, we'll first load the query results into an arrow table. An arrow ensures that the data is structured in a way that pandas can read quickly and efficiently. So this means we can get faster and smoother data handling, making it easier to dive into analysis. So let's run this query. So as you can see here, you can see a small preview of the table with 3 rows of data and the corresponding columns. So you can take a moment and look what's available. So you have to keep in mind that this is just one table, and here we had applied a limit over here. So we applied 3, so here we are only able to see a tiny portion of the entire table. So when working with large data sets, especially in machine learning and AI, it's common to deal with massive amounts of information that won't always fit into memory, especially if you're running a local notebook. So now let's say you want to retrieve all columns and rows from the post question table. So this time we won't apply any limits, so we'll just get the full data set. So let's write that code. So as you can see, we are going to run the same query again. If we compare, it's the same query, but then we are not going to apply any limit. That means we'll be pulling all the data from the table. The code. So now we are sending, what we are doing is now we are sending this query back to our data warehouse. So since we are working with a larger data set, it might take a little longer to process. And here we have loaded the result into pandas data frame. Now let's just run this query. Okay, so as you can see, we have hit a 403 response, 403 error. So as you can see, we have hit a 403 error. It says that response is too large to return. So basically, here's what's happening. Your data warehouse can store massive amounts of data, but that doesn't mean that your local machine or virtual machine or container has enough memory to handle it all at once. So when we try to pull too much data at once, we run into these issues. So while working with large data sets, memory can be a problem. So here's the best way you can handle it. Now, if your data is in a data warehouse and you need to join, filter, or process large tables, do it using SQL inside the warehouse instead of loading everything into pandas. So this keeps things faster and efficient. And once you have chosen the data you need for training, save it in a fast storage option like an SSD or a cloud storage bucket. Because when training models, especially at a large scale, you need quick access to data. So if storage is slow, your GPUs might sit idle, wasting your available time. So always track where your data comes from and what changes it has gone through. This helps while troubleshooting and keeping your work organized. So now in the next example, we'll be combining 2 tables to retrieve a question and its corresponding answer, which we need for our tuning data. So to make sure we are only fetching relevant data, we'll use a where clause, which allows us to filter the results based on specific conditions, ensuring that unnecessary data is excluded. So let's write the code. So now let's just break down this step by step so that you can understand exactly what's happening in the query. So as you can see, first we are selecting data from a public data set, which is Stack Overflow. Specifically, we are pulling information from 2 tables, one that contains questions and another that contains answers. These are the 2 tables. And we are selecting 2 columns, the title and the body of the question, which will combine and call input text, answer, which will call output text. Now to get both the questions and answers together, we need to, this is the question and answer, so we need to join the 2 tables. Now the way we do that is by using a unique identifier. So each question has an ID. And when an answer is accepted, it gets linked to the question via an accepted answer ID. So by joining the two tables on this ID, we make sure that we are matching each question with its correct answer. So now let's define our selection using a where clause, because we don't want to pull all available data. So first we make sure that the question actually has an answer. Then we filter only Python related questions because we are focusing on Python. And at last we'll filter by date. So this is super useful when working with time sensitive data, as it allows us to work with a specific period. And finally, what we do is we limit the number of results to 10,000 examples. So we don't need the entire data set, just enough high quality examples for tuning our model effectively. And at the end, this query helps us to create a structured database where each row contains a Python related question and answer. So let's is equal to let's just run it. So as you see, we have written our query. Now it's time to send it to the data warehouse, just like we did before. So once we get the results, they'll be in Pandas data frame, giving us a structured data set with questions and answers, as you can see. So now here is an important point. Fine-tuning language models using datasets formatted as instructions has been proven to boost their performance and ability to handle new tasks. Simply put, it's a clear guideline that tells the AI what to do. So there are different ways to frame the instructions. First thing, you can set a rule. Second thing, you can break it down step by step. And third, you can provide a procedure or an example. So if only we give the model a question and answer, it might not always know what to do with them. But by adding an instruction, we guide the model on how to respond, and this makes its answers more accurate, relevant, and useful. So let's enhance our dataset by adding an instruction column. So this will just write an instruction template. We are going to use an instruction template. As you can see, we have used an instruction template that provides clear guidance to a large language model. So the template will include a specific instruction, like telling the model to respond like a developer answering Stack Overflow questions. So for example, here's the structure. Please answer the following Stack Overflow questions on Python as if you were a developer answering Stack Overflow questions. So instead of modifying the existing question column, we'll create a new column that combines this instruction with the original question, and this way we keep the original data intact in case we need it later. So let's write the code. So as you can see, first we'll combine the instruction template with our input text to create a new column called the input text instruct. This will help structure our data properly for training. And next we'll split the data into two parts, for training and evaluation sets. So the training set is used to teach the model, while the evaluation set remains untouched during training. And we'll use the evaluation set later to check how well the model performs on unseen data. So next, let's prepare the dataset for tuning. We are going to use Scikit-learn's train test split to divide our dataset into training and evaluation sets. So by default, the split is 80% for training and 20% for evaluation, but we'll adjust this a bit to keep more data for tuning. So let's do that now. Selection, import, train, test split, training, evaluation, test size we are giving it as 0.2, random status, We'll also set a random state to make sure our split is reproducible. So this means that every time we run the code, we get the same train test split, ensuring consistency in our results. So why is this important? Because each time you train your model or run an end-to-end workflow from raw data to tuning, you want to compare results fairly. And if you choose too many things at once, like adjusting the train test split from 80 to 20 to 60-40 and also tweaking multiple hyperparameters, you won't know which change actually affected the model's performance. So instead, it's best to adjust one or two parameters at a time so you can clearly see what's making an impact. You might be wondering why we are not using accuracy as a metric. So the reason is simple. We are working with text and text is ambiguous. So unlike structured data where accuracy is a clear-cut measure, evaluating test-based models is trickier. So instead of accuracy, we'll rely on other evaluation models that make more sense for data, for text data. And when working with large data sets in your data warehouse, one of the best practices is to move the data out and store it in files, like either on an SSD or a cloud storage bucket. So this makes reading the data much faster. Now, a most common question that comes up is which file format should I use for training and evaluation data? So there are several options, and the best choice depends on the size of your data set and how you plan to use it. So for this example, we are using a JSON-L. It's a simple text-based format, but each question and answer is stored as a separate row. So JSON-L is human readable and works well for small to medium-sized data sets. But however, if you're dealing with a larger data set, you'll want something more optimized for performance, and that's where TF record and Parquet files come in. So let's see what these are. So TF record, which is also the TensorFlow record, is a binary format that's designed for efficient reading by computers, making it a great choice for high performance training. And Parquet is another binary format that's highly efficient, especially for handling large and complex datasets during training and tuning. So ultimately, the choice depends on your model framework and personal preference. Both TF record and Parquet are great for large-scale machine learning workflows. So now, while working in an MLOps workflow, it's also crucial to version your data and artifacts. So you'll likely be dealing with multiple versions of your dataset, whether they are stored as tables in a data warehouse or files for training. So keeping track of these versions helps with traceability, number one, which is knowing exactly which dataset was used to generate a particular training file. Next, it helps in reproducibility, ensuring that experiments can be repeated with the same data. And then maintainability, which means managing updates and improvements to your datasets over time. So let's move on to coding. So in this case, we are also going to version the JSON-L file we generated. So to keep things organized, we'll structure the file name using the type of dataset, whether it's for training or evaluation, the name of the dataset, and a timestamp that includes today's date and time to track when the data was generated. So for that, let's first import date, time. After that, let's set the timestamp. Date is equal to date time dot date time dot now. So as you can see, to achieve this, we have used the Python's datetime library, and this allows us to capture the current date and time, ensuring each file has a unique and meaningful name. So that's done. Now it's time to create our JSON file for tuning. So let's do that. So keeping track of different versions of a file is important, especially when working with datasets. So to stay organized, we'll name our dataset as Stack Overflow. So this is related to question and answer problem, and to make sure we always know when a file was generated, we'll include the date in its name, and this helps us manage versions and track changes over time. So now let's generate the file. We have to save it locally using the file name we just defined. So once the file is created, you can find it in your workspace. You just have to go to File, Open, and you'll see it there. So maybe you want to handle versioning differently, such as organizing files by year, month, date, and hour for better sorting. Or if you're working with a JSON-L file, try removing orient is equal to records and lines is equal to true to see how the structure changes. So instead of having each question and answer on a separate line, the formatting will be different. So that was it in this chapter. Now in the next chapter, we'll dive into automation, orchestration, and parameter efficient fine-tuning, which are the powerful techniques to streamline and optimize your workflow. So welcome to our next chapter on automation and orchestration. So now that you have your data, it's time to fine tune a large language model. So keep in mind that the tuning a model isn't just one-time task. You might need to adjust it multiple times to get the best results for your specific use case. So since LLMs are still evolving, experimentation is key to figuring out what works best. So to make things easier, you'll want to automate the experiment process instead of doing everything manually. And in this lesson, you'll learn how to build a machine learning pipeline using an open source framework. This will help you fine tune and deploy your model efficiency so that you can focus more on results and less on repetitive tasks. So before jumping into the code, let's take a moment to talk about MLOps workflows, especially for large language models. So far, we have discussed system designs for LLMs and some basic one-dimensional workflows, but when you're training or fine-tuning a model, the process generally follows a structured pipeline, which are as follows. Number one is gathering training data. So you start by collecting the data your model will learn from. Next, train the model. The model learns patterns from the data. Number three, evaluate during training. So while training, you assess how well your model is doing. Next step is to get a trained model. So at the end of the training, you have a model ready for use, typically saved in a format like TensorFlow Save Model. And finally, deploy the model. So you put the trained model into a production environment where it can generate predictions. So once the model is in production, it can be exposed through a REST API for real-time predictions or used in batch process for large-scale predictions. So the key part here is that evaluation doesn't stop. You keep monitoring performance and updating the training data as needed. So now let's move on to some of the key aspects of MLOps workflows. So there are three important concepts in this workflow. First one is orchestration, which is deciding the order of steps, what happens first, what happens next, etc. Next is automation, which is ensuring the workflow runs automatically so that you don't have to trigger each step manually. And then comes deployment, which is taking the trained model and making it available in a real-world environment. So to put it simply, orchestration means structuring the process so that the steps run in correct order. Automation means you don't have to manually execute each script, everything runs on its own. And deployment means putting your trained model in production where it can generate predictions. So for example, imagine you have multiple Python scripts, one for data preparation, another for training, and another for evaluation. So instead of manually running each script in order, you'd want a system to orchestrate and automate this process. So now let's see some of the tools for orchestration and automation. So to handle this efficiently, we use MLOps framework like Apache Airflow, which is a powerful tool for managing workflows, often used in data engineering and machine learning. And then we have Kubeflow Pipelines, which is a framework especially designed for ML workflows on Kubernetes. So both tools help in structuring, automating, and monitoring ML workflows, ensuring that the entire process runs smoothly without manual intervention. So let's get back to our code. So here we are working with Kubeflow Pipelines, which is an open source framework that automates and manages machine learning workflows, which we saw earlier. So instead of manually handling tasks like data processing and model training, Kubeflow Pipeline streamlines the process. So first we'll import the pipeline package. Let's import first from import from import compiler, import warnings, so as you can see, we have imported the Kubeflow piping package. It includes a DSL, stands for domain specific language, and it is a blueprint for defining pipeline steps. We'll also use a compiler, but we'll discuss more about that later in this chapter. So before diving into complex workflows, let's begin with a very simple example to understand how orchestration and automation works. So for example, imagine that we have a basic Python function that takes a name as input and returns a greeting. So let's say an example where we have the input as Harry and it will output hello Harry. So we have the input. So this might seem simple, but it introduces a core concept of breaking tasks into steps. So Kubeflow is built around two main ideas, which is components and pipelines. So components means individual steps like data processing or model training, and pipelines, which is a sequence of components forming a structured workflow. So for example, first step is pre-processed data, second step is train model, and third step is evaluation results. So managing machine learning pipelines manually is complex, and Kubeflow automates workflows. And each pipeline step runs in a container, which is a self-contained environment that includes necessary software dependencies. So in an ML workflow, different steps need to work together and some depend on the output of the others. So let's create another Python function, which is how are you. So this is the second component, which takes a string as input and uses the output from the first function, say hello. So since the second step relies on the first, they must run in order. First, we get the greeting, then pass it to the next step. So similar process happens in machine learning pipelines. So for example, the first step might generate training data files, and the second step trains a model using those files. So instead of passing large data files between steps, a better approach is to store them in a cloud storage and pass only the file paths to the next step. So this makes the pipeline efficient by reducing memory use, keeping steps independent, and preventing unnecessary data duplication. So as you can see, for this Python function, we also need to use the DSL decorator, especially the component decorator, to let the system know that this function is a Kubeflow pipeline component. So now that we have two components ready, the first component and second component, it's time to design our workflow and decide how these steps will be executed. So we are going to build our pipeline and define how the components connect and run in sequence. So here we are simply creating another Python function, which is called hello pipeline. So let's create that. At dsl.pipeline, hello print this string. Hello task. Recipient. Task. Is equal to hello task output and then return task. So as you can see, this function takes a recipient's name as input and defines the order in which our component will run. So since we have already discussed the execution order, we know that our first component is say hello. So we'll start with that. This function will take the recipient's name, inject it into the component and execute it. Next, we move to the second component, which is the how are you, which will take the output of the first step as its input. So this means the hello text generated from say hello function will be passed into the how are you function, ensuring the steps are connected. And finally, we return the output from the second step. So now to make sure that the system recognizes this function as a pipeline, we use a decorator to define it as a sequence of steps. So this tells Kubeflow that hello pipeline isn't just a regular function, it's an orchestrated workflow that needs to be executed in the specified order. So now let's move on to building our pipeline. So a pipeline is simply a collection of components working together in a defined sequence. So it controls both the order of execution and how data flows from one step to another. And in other words, data moves downstream through the pipeline where each step can use the output of the previous one. So as we defined our components already in pipeline, it's time to compile everything into a file. So for that, we'll use a compiler which generates a YAML function. So let's do that. Compiler. So as you can see, we have used the compiler which generates a YAML file. So YAML file is a human readable format used to store configuration details, including sequence of pipeline steps and many dependencies they require. So one last thing is our pipeline needs an input name when it runs. So since we are greeting a person with hello, name, how are you, we need to define this argument before execution. So let's do that now. First I'll write the code and then I will explain it to you. Arguments. Unit is world. So as you can see, during execution, these arguments are provided to our pipeline. Here we have a pipeline argument, and in this case, the recipient is set to world. So once the pipeline YAML file is generated, you can open and review it to see how parameters are structured. So now let's run the cat command on our pipeline YAML file. Let's try the cat command. As you can see here, just a bit. Yeah. So as you can see here, this allows us to see the components we defined along with other details related to the execution dependencies. So with the YAML file ready, we can execute it in different environments. So if you are using Kubernetes, you typically need to manage the cluster yourself, which involves handling deployment and operations. So instead, you can use a managed service like Vertex AI Pipelines, which runs the YAML file for you in a serverless environment. So to do this, you would use the Cloud AI Platform library and import pipeline job. So let's do that now. Let's write the code. So from Google Cloud AI Platform, import pipeline job. So we have imported the pipeline job from google.cloud.ai platform. We'll finally launch this job using job.submit function. Submit all. So you can run this on a Google Cloud using Vertex AI Pipelines, which is a serverless platform built on top of Kubernetes. So you don't have to worry about managing machines, virtual machines, or Kubernetes clusters. All you need to do is send a YAML file and Google Cloud handles execution for you. So once the pipeline runs, you can see the execution Vertex AI Pipelines. So here you will find the two steps we created, say hello and how are you, along with the parameters, their types and values. So if you check the second component's output, you'll see the final result is, as you can see here, hello world, how are you? This view helps track the pipeline's execution while also giving a clear picture of how the components interact. So let's look at a real-world machine learning pipeline and why it's useful. One major advantage is reusability. Once built, a pipeline can be used again or shared with others. For example, if you create a pipeline to process data and train a question and answer language model, so a colleague with a similar task can reuse it instead of building from scratch. And now in the next example, we'll use an open source Kubeflow pipeline to fine-tune PAM2, Google's foundation model. And since the pipeline is already built, we only need to adjust some parameters, making the process faster and efficient. So now that we have our training and evaluation data, we can use them to fine-tune a POI models to supervised fine-tuning. So one of the greatest things about pipelines is their reusability. So instead of building everything from scratch, we can reuse it. So let's write the code. And now let's import the path to the pipeline file to reuse. So here you can see the path to the pipeline file. So I hope you remember the YAML file we created earlier. So this is where you can find it for this pipeline. To run the pipeline, we need to set up some configurations, which mainly involve specifying the required arguments. So first, let's start by choosing a name for our model. But before that, we already learned why versioning is important. So first, we'll use a date timestamp in a model name to keep track of when each model was trained, so that it can easily go back and check the past versions. So let's do that. Let's import date time. So the timestamp. Name. Now there is also some key settings we can do. So one is the training steps. Just a second. So basically training steps control how many times a model updates its internal parameters while learning. Let's set it first. So training steps, we'll set this as 200. Evaluation interval, we'll set it as 20. So as you can see, training steps meant each step feeds a batch of data into the model. It updates its settings and measures the error. So this is different from epochs which go through the entire data set. So for question and answers, the best practice for this power model is between 100 and 500. For time being, we have used 200 for now. Now another important setting is the evaluation interval. Now evaluation interval means it decides how often the trained model is tested against the evaluation dataset. So here we are using 20 by default, but you can change it based on your needs. So just like we did for our Hello World pipeline, we need to define the arguments our pipeline will use when it runs. So let's do that. Let's load the project ID and credentials. We'll also set the region. Just a second, there was a small mistake. Yeah. Set the region to US Central 1 itself. Now the next step is to define the arguments of our pipeline. So let's do that. So these arguments are important because they are used by the system during runtime. Meaning when the pipeline runs, it takes in these values and processes them accordingly. So for our pipeline, the key arguments include the model name, the region where the workflow is executed, and the model used for the parameter efficient fine-tuning. So as you can see in this case, we are using a POM family model called Text Bison, which is well suited for question answer tasks. The model version is 001. Other important arguments include the project ID, the number of training steps, which we have set to 200, the location of our training data, the evaluation interval, which we had set to 20, and evaluation data URI, which tells the system where to find the evaluation dataset. So these arguments make the pipeline flexible. So when setting up a pipeline, you can define different arguments, and the best part is they can be updated without modifying the entire pipeline. So for example, if you have a new dataset, you simply change the dataset argument instead of rebuilding everything. So similarly, if you want to fine-tune a different model, you just update that parameter, that's it. So next we need to set the pipeline route, which is where all the artifacts generated during execution will be stored. So after that, we define a pipeline job, which tells the system how to run the pipeline and what arguments to use. We'll write the code. So as you can see, we have also enabled caching over here, which helps optimize execution. So if you rerun the pipeline and a step has already been executed before, it won't run again unless the code or inputs have changed. So this saves time and resources by skipping unnecessary computations. And finally, we submit the job, but we won't actually run it now because the execution of this pipeline would take a lot of time and it requires a very powerful hardware. So for now, we'll just set up everything without running. But I'll just show you what the result would be if we run this code. So as you can see, this would be the output displayed if we run the code successfully. So this was it about this chapter. In the next chapter, we'll dive into deployment. After fine-tuning a model, the next step is to deploy it so it can be used in our LLM system. So hey all, welcome to the last chapter. So here we'll use the tuned model to make predictions. Before integrating it into a real-world application, we need to ensure that it performs reliably and safely. So this includes checking if production data matches the training format, analyzing responses for safety attributes, and identifying sources behind predictions. So again, we need to set up our credentials and project ID again. So let's do that. From utils, import, authenticate. examples and project ID. Now let's set the region. US Central 1. So we are done setting up our credentials and project ID as well as region. Now here also we are going to use Vertex AI SDK and specifically the text generation model that we recently fine-tuned. So let's import Vertex AI from Vertex AI language models, import text generation model. So now let's go ahead and set up the Vertex AI SDK. We'll configure it with the project ID, region and credentials. So let's do that. So we have set up everything. So now before going deep into it, let's first dive into model deployment and know what it really means. So deploying a machine learning model can mean different things depending on how you plan to use it. Sometimes you just need to run predictions in bulk, and this is called batch processing. So for example, if you're analyzing customer reviews, you don't need results instantly. You can wait until the end of the week, gather all the reviews and process them in one go. So it's efficient and works well for large dataset. But if you need real-time predictions, like in a chatbot that answers coding questions, you will want to deploy the model as fast as the REST API. So this way, when a user asks something, the request goes to the model, gets processed, and a response is sent back instantly. It's all about low latency and quick responses. So to set up a REST API, you can use Flask or Fast API to wrap your model and then package it in a container for easy deployment. So whether you go with batch processing or a REST API depends on your needs, which means bulk predictions versus instant responses. Depends on what you want. So to interact with our API, we need to run a few lines of code to retrieve the endpoint of a model. So let's write that. Model is equal to text generation model from pre-trained text bison 001. So the endpoint is simply the URL of the REST API where our model has been deployed in the cloud platform. So since our model is now packaged and live, we need to tell the system which model to use for predictions. So think about when we fine-tuned the text generation model. So this was one of the parameters we defined in our pipeline. So now using the SDK, we can easily fetch the list of all deployed models and select the one we want to use for making predictions. So let's do that. We have to get the list of multiple models executed and deployed. So list tuned models is equal to model dot list and model names try tuned models print type. So this helps to route the traffic to different endpoints. So here we have used the list of fine-tuned model names to fetch their endpoints. Since we have run the pipeline multiple times, there are several endpoints available. Now let's bring them out and see what we have. So as you can see, within our project, there are 3 endpoints currently. So as you can see, within our project, there are 3 endpoints currently active in the US Central 1 region, which has the specified location as US Central 1 region. So to handle incoming requests efficiently, we deployed multiple models so that the workload is distributed across 3 different instances. So instead of overwhelming a single model, we are using a simple load balancing approach to direct each request to one of the available endpoints. So this ensures smoother performance and prevents any single model from being overloaded. So here we'll be working with a random library to randomly select an endpoint from our list. So let's import the random. Tuned. Model select. Tuned models. So this chosen endpoint will be the one we use to request a prediction. So after selecting a deployed model at random, the next step is to load it so that we can use it for predictions. Let's do that. So getting a prediction simply means sending a prompt to the API and receiving a response generated by the model. So once the model is loaded, we can go ahead and craft a prompt to see how it responds. So since we have fine-tuned our model using the Stack Overflow dataset, it makes sense to test it with a Python-related question. So the goal is to keep our inputs as close as possible to the data the model has already seen, which helps ensure more accurate responses. So let's try with a simple test question. Let's give a prompt. How can I load a CSV file using pandas? So at this point, we have set up our prompts and loaded the API. Now we can send the prompt to the API and get a response. So to do this, we'll use the Vertex AI SDK, where we simply call a .predict on our deployed model, passing in our prompt. So the request is sent to the API, processed by the model, and we can receive a response in return. So let's write the code for that. Response is equal to deployed model dot predict prompt print response. So as you can see, this is the response we have got. So large language models can vary in response time based on their size and the length of the input. So the bigger the model, the longer it usually takes to generate an answer. Similarly, if you provide a longer prompt, the model needs more time to process it and return a response. This means that latency, the delay before you get a reply, can differ depending on how complex your request is. But here, as you can see, the response we have got is quite lengthy and it's hard to read. So the thing is, we have to format it now. So let's see how to format it. So here we'll be using pprint, which makes the response easily readable. So let's import pprint from pprint. So from pprint, import pprint. So now when working with an API, you can send multiple prompts and receive multiple responses in return. However, since we only sent one prompt, we are getting back a single response. So let's take a closer look at it by printing it out in a structured format. So we can now send multiple prompts to see the multiple responses. So let's just do that. So let's write output is equal to response dot prediction response 0, print. So as you can see here, this response contains a lots of details, including citations. As you can see, there is citations as well as scores. So for now, let's break down the response further and examine the second object. So let's do that. Let's code it. Print it. So as you can see, when we print it, we'll notice that the output only contains one object, but within that there are multiple keys holding different pieces of information. So we have content that includes attributes, which are safety attributes. And the content itself is a response generated based on a question. And essentially it's the answer to the prompt we provided. So now let's extract the response, which is the actual answer to a question from the output. So let's code for that. So final output is response prediction from content and print final output. So let's print and see. So as you can see, there it is. The model has generated a response providing the answer to our question. So we had asked the question, right, how can I load a CSV file using pandas? So finally it has given a final answer that to load a CSV file using pandas, you can use the read CSV function. This function takes in all the details. So finally we have received the correct answer for our question. So now deploying a model isn't just about getting it up and running. You also need to track its performance. This means checking how often predictions are made. So making sure it stays accurate and ensuring it doesn't produce biased or harmful results. So scalability is also important. That's another factor. So instead of just launching it for everyone at once, you can start by sending only like 5% of traffic to the model and gradually increasing it. You should also discuss response time with stakeholders, like should it reply in 100 milliseconds or is 2 seconds okay to get a response, etc. So for example, if it's too slow, you can use a smaller model, switch to GPUs or deploy closer to your users to speed things up. Now, another key thing to keep in mind is the input data consistency. So if the model was trained using both instructions and questions, but is now only getting questions, this mismatch can affect accuracy. So to fix this, we need to format the data the same way it was during training before sending it to the model. So let's do that now. So let's build on the instruction we created earlier and introduce a new question. So let's code it first. So here we are providing it an instruction. And we'll just give it a question. The question is, how can I store my TensorFlow checkpoint on Google Cloud Storage? So as you can see, we have an instruction, a question, and by combining them, we can create a prompt. So let's create a prompt where we'll combine the instruction. Here we have combined the instruction and question, and we have created the prompt. Now if we print the prompt, we can see that both elements are now merged into a single input. So let's just print a prompt. Print the prompt now. So as you can see, we have a combination of instruction as well as the prompt. So this structured prompt aligns with the format used during training, making it more effective. Now we can take this newly formed prompt and send it to API, following the same process as before. So our deployed model will run a .predict function. Let's just write the code. Final response is deployed predict prompt. So once we get the response, we will extract the answer using the content key. So we are extracting the output using the content key to retrieve the relevant information. Now let's just print the output to have a closer look. So let's print the output. Okay. So we can see that the responses are well structured and sounds something like a developer would write while answering a Stack Overflow question. But there's more to this output than just one response. It includes safety attributes. So one of the challenges with large language models is that their responses can sometimes be unexpected. Like they might generate content that is offensive, biased, or factually incorrect. So because these models are also so flexible, predicting every possible response is difficult, which is why careful testing and evaluation is essential. So to help with this, the PAM API fine-tuned includes safety attribute scoring. So this feature, like we saw the scoring before, so this feature allows us to assess the model's output and set confidence thresholds, essentially defining limits for what is considered safe or appropriate. So these thresholds help filter out potentially harmful or misleading responses before they reach users. So now let's explore this further by writing some code on it for safety attributes. So let's write the code first and then we'll explain what it is. It is equal to response dot prediction key attributes blocked. So now instead of using the same key as before, we'll be working with a new key which is called safety attributes. So this allows us to check if any part of the response was flagged or blocked by the responsible AI system. So many AI service providers have built in safety checks that review a response before sending it back to the developer or user. So if the system detects an issue like content that violates safety guidelines, it may block the response entirely. So let's just check the response was blocked by looking at the safety attributes and printing the result. So yeah, let's just print the result. Print blocked. So as you can see, this is how we check if any response was blocked. So if it had returned true, it means that it is blocked. Or some of the responses were blocked, but as you can see, it has returned false, which means none of the responses are blocked. Developer, you have an extra layer of control when it comes to checking for safety issues. The response you receive includes probability scores for different categories, which you can use to set your own custom threshold. But however, it's important to remember that these confidence scores are just predictions. They provide useful insights, but they shouldn't be the only factor in determining reliability or accuracy. So you can think of them as one tool in your safety toolkit rather than a final decision maker. Now in this second level, you can take the safety attributes and scores and tailor them to your specific needs. So let's take a closer look at that. So we are going to use the key safety attributes from our response to retrieve safety related details and their corresponding scores. So let's write the code first. Safety attributes is equal to response dot prediction safety attributes. Now to make the output easier, we'll use pprint again to display these attributes clearly. So let's do that. Let's use pprint safety attributes. So this is the response that we got. Now let's just see what it is. So first we can check whether the response was blocked or allowed. So in this case, blocked is false, which means it wasn't blocked, it is allowed. Then we have different safety categories. As you can see, there is finance, politics, sexual, etc. And they also have the ratings like severity scores. So as you will notice that the probability scores for each category, these scores range from 0 to 1. 0 is minimum and the highest value is 1, and it indicates how likely the content is to be unsafe. So for example, if a category has a score of 0.1, so as you can see harassment has 0.1, that means there's a very low chance that the content is unsafe. The scores are rounded to 1 decimal place to make them easier to interpret. And another key detail is the severity score, as you can see here. So it's important to note that while probability scores estimate the likelihood of unsafe content, they don't necessarily reflect how severe the harm could be. So a piece of content might have a low probability of being unsafe, but still pose a high risk if it does turn to be a harmful, content. So keeping this distinction in mind is crucial when evaluating safety attributes. So now when working with Gen AI, the goal is to create unique content, right? Rather than duplicating whatever material is available. So to minimize the chances of repetition, it's important to design systems that actively reduce risk. Now, one way to do this is by using citation metadata, which allows you to check if any references or sources were used in the response. So this helps ensure that the content remains original, but also providing transparency about any external information included. So we'll see how that's done. So let's write the code first. Citation equal to response prediction response citation metadata citations. So we can extract citation details from the model's response, and within that metadata, we can look at the reference sources to verify if the information is backed by existing citations. So let's just preprint again to see if any citations appear in the response. So let's just print it, preprint citation. So if there aren't any, it means that the content is original. So as you can see, they haven't found any citation, and it actually gave us an empty set. But if a citation is found, the model will show the source, like from where the information came from. So as you can see, this content is original. So that was it, guys. Congratulations on completing this course on LLMOps. You have gained a solid foundation in the fundamentals, learned how to prepare data effectively, mastered orchestration and automation with pipelines, and also explored deployment strategies to bring LLMs into production. So by applying these skills, you are now equipped to optimize, scale, and manage large-scale models efficiently. So keep experimenting, stay curious, and continue building innovation AI solutions. And best of luck on your LLMOps journey. Thanks for watching.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.